Hello friends, welcome to my YouTube channel, Code with Dharmaveer, and in this DSA series we are going to cover the topic time complexity. So we'll be discussing this time complexity in detail. So time complexity basically describes how the execution time grows with the input size n, and this time complexity is independent of machine or language. So that's it's not dependent upon your machine or the language. You should always consider the worst case unless it's explicitly asked otherwise. So you have to always look for the worst case when you are doing the analysis. Now we have some of the common time complexities that you must know. The first time complexity is O of 1. The O of 1 is typically use case we find in hash lookup, array access. So inside it is a best possible you can say time complexity. The second case is the O log n, O of log n. That is also a binary search or heap ops. Okay, so the insight is that it requires a sorted or tree structure. So then whenever you are talking about the sorted or tree structure, then that means the complexity is O log n, O of log n, and it is basically a binary search heap ops. And the third complexity is O of n. It's also a single pass, and it's basically a optimal, usually optimal. So you should always look for a single pass or O of 1 type of complexity. The next type of a complexity is O of n log n. It is used typically in sorting and divide and conquer. So it's often unavoidable. You can't avoid it. Next type of complexity is O of n square. That is typical use case in nested loops. It is acceptable for only a small size of the input n. The third is O 2 raised to the power n. Then that is basically a backtracking, and it is needs pruning or optimization. So how to calculate this time complexity? And if it's asked in interview, then you have an example one, like you have, if you have a single loop just like a for loop for int I equal to 0, I is less than n, I plus plus, then that is a constant work. This loop is doing a constant work, and the time complexity is O of n. So explanation is that this loop runs the constant work each time. That means a constant work is being done each time. The next example is nested loops. For the nested loops, you have two for loops. First one is outer loop and second one is inner loop. So you can see that for I equal to 0, n I is less than n, I plus plus, and for the second loop j equal to 0, j is less than n, j plus plus. It's a constant work, some kind of a constant work you are doing there. So basically the time complexity is here O of n square. So the explanation is that the inner loop runs n times for the each outer iteration. That means for the each outer iteration, the inner loop runs n times. The third example is dependent loops. So dependence loop is, you can see that the you have a first for loop, then you have a second for loop that is dependent on the value of I, and this is also doing a constant work. So for these kinds of loops or these kinds of conditions, we have a time complexity as O of n square. So roughly O of n square divided by 2 operations. That means you have ignoring the constant as well. So basically the time complexity for such kind of operations is O of n square. Now you have another example, fourth one, that is logarithmic. So logarithmic, you can see in the loop where n is greater than 1, and you are every time dividing the value of n by 2. So for such kind of input where you are dividing by 2, the logarithmic kind of thing is happening here, and for such kind of thing is the time complexity is O log n. So every time, so each input size is getting half for each iteration. Input size half for each iteration here. You can see that. Now the next complexity is recursion type complexity. So in that you have a binary search and a merge sort. For a binary search, you have T of n is equal to T of n by 2 plus O of 1. So that gives you O log n, O of log n. And for a merge sort, you have T of n equal to 2T of n by 2 plus O of n. So that gives you O of n log n. Now let's talk about the space complexity. So space complexity is basically the extra space or a memory used excluding the size of the input unless it is stated. So that means your whatever the extra memory space you are using, that is basically space complexity, and it includes auxiliary data structures, recursion stack, and temporary variables. Let's come to the example of space complexity. First example is constant space. There you can see that you have a sum variable in sum equal to 0, and there you can see that for this the only a constant variable is used here. So for this the space complexity is O of 1. So that's how you are going to calculate the space complexity. Now, the another example is if you are using extra array, in that you can see that you have a temp array, and that size of array is new int of n. So in that you are using the time or space complexity as O of n. Then you have a recursion stack. In that you can see that you have some method, and in that method you are basically having a node, and if the node is null then you return, and if you want to traverse to the left or you want to traverse to the right, then you have the other function, other method over there, you can see. And for such kind of recursion stack you have a space complexity is O of h, where h is the height of the tree, and in this case the worst case is O of n, and the best case is a balanced one, and that is O of log n. So you have a balanced case where this is O of log n. So for this kind of quality DSC contents, please like, share and subscribe. Thank you. Thanks for watching this video.